Good afternoon, everyone. I am Dr. Mahendra Kumar Gupta from NIT Jamshedpur. Today, I am going to give my presentation on PD Observer design for descriptor systems with unknown inputs, application to infinite bus system. So, there are few terminology in the title of my talk, and I will explain them one by one. So, the first one is descriptor system. Descriptor systems are also called systems governed by differential algebraic equations. So, there are algebraic equations and there are some differential equations, and descriptor systems are implicit combinations of difference, differential and algebraic equations. Descriptor systems arise in various applications where system dynamic is constrained by some algebraic equations. Now, the second terminology is an observer. Observer is a mathematical model that is used to reconstruct the system states using input and output information of the system. So, observer is just a mathematical model. It takes input and output of the original system, and its output asymptotically converges to the true state value of the system. Now we come to proportional derivative observer. So observer is proportional derivative PD observer if derivative of the output data of the given descriptor system is used as input of the observer. Now what we are going to do in this work, that we are going to design PD observers for linear descriptor systems with the presence of unknown inputs. So we are considering systems where there are unknown inputs, and we will design PD observers for that. Now what we do in this order, we will provide sufficient conditions for the existence of the observer in the form of system coefficient matrices. Now we will calculate the observer matrices. We will construct some matrix equations, and we will solve some matrix equations to construct some observer matrices. So we will use two methods. One is pole placement method, and another one is LMI, solving linear matrix inequalities. Now, to show effectiveness and applicability of the results by real life application to an infinite bus system. So we will show our effectiveness and applicability of our results. Now, this is the abstract form of linear descriptor system with unknown input. It is given by system 1. So there are two parts of the system. One is 1A and second one is 1B. So the 1A is called dynamical part and 1B is called output part. Here are system description. X is called as semi-state. U is control input vector. So that is the vector, that is the value that B provide to the system. Y is the output vector. So this is the value that we can measure from the system. There are some measuring instruments for that. Now V is unknown inputs. So these are the inputs which are affecting to the system, but we don't know the value of it. E, A, B, C, and F are the known and constant matrices. Now, throughout our work, we will assume two assumptions, assumption A1 and A2. These assumptions are given in the form of some rank conditions directly on the system matrices. Now we convert the research problem in mathematical form. So mathematically, we can say that problem is to design NT, L, and M such that system 2 becomes an observer for system 1. So system 2 is written as following, and system 1 is already written in the previous slide. And if system 2 becomes system observer for system 1, so we have to design the coefficient matrices in such a way, such that, which means that x hat should approach to x as t goes to infinity for all initial conditions of system and all initial conditions of the observer. Now, before solving the problem, we will use some lemmas, lemma 1 and lemma 2. So lemma 1 gives a lower bound on the multiplication of two matrices, lower bound on the rank of multiplication of two matrices. And lemma 2 says that if there is a matrix pair E and C, and it satisfies some rank condition 4, then we can definitely construct a full column rank matrix R which satisfy a rank condition given by equation 5. Now this lemma 2 we have taken from our previous work, and lemma 1 we have taken some basics of linear algebra. Now this is our main result of the paper. It says that If system 1 satisfies the assumptions A1 and A2, then there exist matrices N, T, L and M such that system 2 becomes an PD observer for system 1. So in this proof, we also give our algorithm to design these matrices so that 2 becomes observer. So first we take error E equal to X minus X hat and we get the dynamics E dot equal to NE. Now we can say that if matrix N is a stable matrix, if it is Hurwitz stable, then error will asymptotically approach to 0 and the and 2 is an observer for 1. Now in construction of 6, we have used 3 equations 7, 8 and 9. So in 7, 8 and 9, what we have done is that now we will solve these three equations 7 and at 9 and we will find the value of unknown matrices such that n is a stable matrix and then our problem is solved. So in the remaining part of the proof we will only solve these three equations and then our proof is completed. So I have converted the problem in two steps. In first step, we are solving equation 7 and 8. And in the second part, we will solve only equation 9. So in 7 and 8, what we get, so how it is done? It is done that we are using the assumption A1 and using the assumption A1 and lemma 1, we get equation 12. So if we use these two assumptions, we will get lemma 1. So here in the my presentation, I am proving this theorem in a short way, and the detailed mathematical proof is given in the paper. So using A1 and lemma 1, we get the matrix equation 12, and if it satisfies the matrix equation 12, then according to lemma 2, we can apply lemma 2 here, and there exists a full column rank matrix R, so that it satisfies the 13. Now 13 is a necessary and sufficient condition for the existence of M, so that I minus T equal to MC, where T equal to RT node. So in this way we construct TM, and these all matrices will satisfy equation number 7 and equation number 8. Now we have to calculate, we have to solve 9. So in the second part of the proof we will solve 9. Now in 9, T is already solved and we solve it for L so that N is stable. So let us go to step 2, and step 2 says that if we use assumption A2 and lemma 1, we end up with the matrix equation 15, which says that, which eventually converted to the equation number 16, which says that matrix pair Ta and C is detectable. Now the system, if system satisfy the condition A2, then matrix pair Ta and C is detectable pair, and since it is a detectable pair, let us go back to the matrix equation 9. So if Ta and C is detectable pair, then we can find a matrix L so that N is stable. So from the theory of pole placement, using the pole placement technique, we can calculate such L matrix. Now let us come to the another approach, which is called LMI approach. So this problem is can also be converted to linear matrix inequalities, and we can use MATLAB to solve linear matrix inequalities. There are certain LMI toolbox. So let us take a Lyapunov function. Lyapunov function is V equal to ETPE, where P is a positive definite matrix. Now using equation 6 and 9, we put the value of E dot, which is the derivative of error, and we end up with 17. Now 17 says that if differentiation is negative definite, if a Lyapunov function is positive definite and its differentiation is negative definite, then the error dynamics is asymptotically stable. So for this we have to solve the LMI 19 and LMI 18. Now from the solution of 19 we get the value of L tilde, and from L tilde finally we get the value of L. So we have converted the problem to LMI because solving LMI is easier in MATLAB. Now let us take one example on infinite bus system. So this example we have taken from this paper, Damin Coin, and where the same system is considered, and they have shown some other results. And we are taking, if we make a mathematical model of this system, we get the system 20. System 20 is written as following. Now let us come to the description of all the variables. So x1, x2, and x3 and x7 stand for generator angles. X4, X5, and X6 represent the generator speed. U1, U2, and U3 are mechanical powers. M1, M2, M3 are inertia. D1, D2, D3 are damping forces. And Y's are admittance and VI's are potentials. So this value we have taken as it is from the published paper only for our simulation purpose. Now we see that available measurements are only generator angles. Further, an unknown input load is also considered here. Now, if we convert this problem, this system 20 to the form of matrix format, then we see that we can convert the matrices as written following. Now see, let us notice this, that the last equation of system 20, there is no differentiation involved. So it is algebraic equation. So rest equations are differential equation and this equation is algebraic equation. So that is the reason this is called differential algebraic equation, means descriptor system. Now when we checked on MATLAB, we see that all the these matrices, they satisfy the assumptions A1 and A2, so that we can proceed for the calculation of observer matrices, and we have calculated our matrices in this way, and then we have solved the system. Now since x1, x2, and x3 are already achieved from output part, we simulate, we show our results only for x4, x5, and at x6. Now we see here that red line is the true state of the original system and blue dashed line is the estimated value of the system, and we see that it satisfies the condition of observer that as t goes to infinity, t tends to infinity, estimated value of states, they approaches to the true value of the states. So we say that the similar results are for x4, x5, and x6 in figure number A, B, and C. Okay, so till now what we have done, we have designed proportional derivative observer for linear descriptor systems in presence of unknown inputs. How we did it? We converted the problem into matrix equations 6 and 7, and then these matrix equations are solved by different approaches. So we have used two approaches to solve the differential equation. These are the references that we have used in our work. There are more references given in our paper. Thank you very much. Thank you for listening carefully.